One node, yes, okay. So we end on the theorem that for any metric space, there exists completion unique up to the isometry. And we construct this completion on week ago, but I don't prove this fact, the uniqueness up to the isometry. So let's we have, but it is very simple. Let's sum metric space and we have, for example, two completion and y d and z w, it's matrix, two completions. But by definition, what we have? Definition of complete. There exists y0 in y and z0 in z such that y is isometric to x and z0 is isometric to x. So because these all spaces are isometric, the full isometry, so we can construct the action phi from the action. And we know that the closure of y0 is y and the closure of z0 is z. So what we need, it's only to extend our b action on the limit points, yes? We have a b action between y0 and z0 and it's sufficient to extend our b action on the limit points. So if, for example, y is a limit point of y and y small is not from. So there exists, for example, the sequence yn0 from the y0 capital such that this sequence converge to the y small. And we have the action between parts of our spaces. So we define z0 as image of phi on yn0. Because it is isometry, so we obtain that the coincide this metric is the same as, and this tends to the 0 as n and m tends to the infinity. So we obtain immediately that is fundamental and define phi of y as limit phi z and 0. Fundamental and z is a complete space, yes? Z complete. So there exist limit z and 0. And we define it as, for example, z. So we can define the element z as image of element y from space y. And this is construction is correct because if we take another, here we have some not strictly definition because we can take another. If we take another sequence y and 0 prime such that to the 0, then we can construct so intersection of these sequences. We can take primes with standard method, here without prime. And this new sequence, of course, tends to the y. So we obtain that the image of this sequence, phi etc., phi y and 0, phi y and 0 prime, of course, converge. So they have, so the limit is unique. No definition, yes, construction of the z, not definition, but construction. So the construction of element z of z is correct. So this is the end of the proof. But one remark, it is this construction we can't use for the norm space. The norm space is a partial case of the metric space, but this construction of completion do not preserve the linear structure. You can see when we construct this by embedding to the space of bounded functions, this embedding do not preserve the linear structure. So for norm space, if we want to prove that the norm space is for any norm space there exists a completion, so we must use another construction, another method. But there exists, and for any norm space, there exists a completion which preserves linear structure. Okay, yes? So, and I remind that the complete norm space are named as Banach space. And, but we shortly consider another class of spaces. Why we need a better class of spaces? Two historical questions. So I remind that if norm space is complete, then we name X is Banach space. Banach space, good spaces with norm and complete by definition, but for applications, the properties of Banach space sometimes insufficient. So two historical questions. First, existence of closed complement. What is the question? Let X Banach space and X0 is closed subspace. Of course, because it is closed, it is immediately obtained. It is simple exercise is Banach. So it is too complete. Yeah. Question. Is there exist xy closed subspace of X? Important property to close subspace of X such that we can represent our spaces direct sum of subspaces. It is very convenient structure if you can divide your space into two subspaces, so you can consider, for example, complex problem in whole space in subspaces. So it is the question. So the common answer for unfortunately no. Example, you can try to prove it if you want. C0, which is lies in L infinity. It is complete space, complete and complete, so it is closed. But there are no closed complementary. And second question, approximation. More precise, existence of basis. What we call basis. So there are in infinite dimensional spaces, there are two typical different definitions of basis. First definition, it is so-called algebraic basis. Or Hamil. Let X linear space with infinite dimension system so I take Greek indexes, so I want to emphasize, as I said, that this system may be not countable. Is Hamil basis if first it is linear independence, independent. What we mean if we define the linear independence of the infinite system? How we define the linear independence of infinite system? Who can answer this question?
Infinite dimensional basis.
No. The linear independence of infinite system, it is any finite subsystem is linear independent. Any finite subsystem is linear independent. Yes. And second property, for any x, we can obtain the sum. But finite sum. So it is so we do not need for example, norm structure. It is the definition for any linear space. Any vector can be represented as a finite sum. Theorem state that for any linear subspace within infinite dimension, the Hamel basis exist, but it is useless theorem and useless because it is not. We can only claim that it exists, but we have no method to construct it. So it is not a constructive notion. And for applications, the Hamel basis is useless notion. So theorem states that it exists, but you cannot construct. We have no method to construct it, maybe except the space C with double zero index. In C double zero, we can construct. But another definition, that X is separable normed space. So countable system EK, K from 1 to infinity. Of course, we consider infinite dimensional situation is a Schauder basis. And then by default, if we say basis, we mean Schauder basis. If first it is linear independent, and second, for any x from this space, there exists unique representation. X equal CK EK. CK is from our field, scalars, R or C, depends on our linear space. And what we mean if we consider the infinite sum, the partial sums. So you see that here we use the norm. The partial sum tends to our vector x. So this difference, the norm of this difference, tends to the zero. So we can obtain the method of approximation. We can approximate our vector x with finite sum. And the question, why I use this? From the definition of Schauder basis, if it exists, our space immediately must be separable. Why? Because we have a countable set of vectors, yes, and we know that the norm is a continuous function. So we can change, for example, in real space, you can change these finite sums on sums with real coefficients, or not real, but rational coefficients. So all this set of finite sum, and for example, ck from rational numbers is countable. So we have a countable dense set. So if we have Schauder basis, our space must be separable. Question: if for any separable norm space exists Schauder basis. The common answer, unfortunately, the same, no. The example is not simple. The first example of space without approximation, so we name this space without approximation. First example, it's about this year, 1972, famous specialist, Enflo. He construct the example of separable Banach space without basis, and prove that there in this space there is no basis. So as we see for these two questions, for these two examples, that sometimes the Banach space are not good. So we need some another class, and our topic of lecture today is Euclidean. Euclidean and Hilbert spaces. So I think that for you it is not unknown.
Sorry, I have
Yes?
a question.
Yes.
Why is the space you constructed is dense in with a rational coefficient?
Finite sum, and the rational numbers is countable, and
Yes.
you can, it's constructed as and countable union of countable sets is countable.
Yes, I know that is countable, but why it is dense?
By definition of Schauder basis. Schauder basis means that you can approximate any x with the finite sum, yes? And norm, as I say, is a continuous function. So you can change this coefficient for rational coefficient, for example, in real space. And it will be close. For example, if you find, if exists some sum ck ek, for example, such that the norm x minus ck ek n less than epsilon, and ck are real, yes, for example, I consider that such for a real linear space, then exists ck tilde rational such that x ck tilde ek, for example, less than 2 epsilon. Because it finite sum, I change ck minus ck tilde, for example, less when epsilon on divided on n. I think this is sufficient for you.
Yes.
So and in complex space, you take alpha plus I beta and all these real parts and imaginary parts from rational numbers. And again, we obtain the countable set.
Yes.
So is it clear?
Yeah.
Because
Thank
first step you approximate by epsilon by definition of Schauder basis, and then you change your, for example, real coefficients on rational coefficients, and you have approximation up to 2 epsilon.
Yeah.
Okay,
you.
yes?
Yes.
So we consider Euclidean and Hilbert spaces, and we show that for all these questions, for Hilbert space will be positive answer. We construct the closed complement and we construct bases. And moreover, we show that for example, for quantum mechanics, all models, Heisenberg models and Schrödinger models are equivalent. Heisenberg models is so-called matrix mechanics, and Schrödinger models is so-called wave function models. And when the quantum mechanics arose about 100 years ago, there was some argues about what is the model is more correct. But from the one theorem for Hilbert space, it implies that these models are equivalent. It's some spoil. So definition. And for Hilbert Euclidean space, I use another letter. Let H is linear space or field, as we say, K and R or C. Yeah? And function of two arguments. So it is from H to from the direct sum H of on H to our field is inner product or scalar product if we have three properties. First, for any x from H, the scalar product x of x is non-negative, and this scalar product can be zero if and only if x is zero. Second, it is linear on first argument. I defined it as mathematics. Very often physics like to define it is linear for the second argument, but I defined it as a linear and z. Alpha x plus beta y scalar product with z equals alpha x scalar product z plus beta with scalar product yz. And second, it is semi-squilinear. So for any x, y from H, I write it for a common situation of complex space. But of course, in real space, the value of scalar product is real, so it doesn't matter for this complex conjugate. Yes. Is this notion is known for you? How? In what details I need to explain some things, or we can something omit?
I think everyone had this notion on the first.
Okay, if we prepare some questions, so we can discuss it. But properties, yes, properties of scalar property. I remind. First, it is Cauchy-Bunyakovsky inequality, yes? Also called by, I think, in English more often say Cauchy-Schwarz. So it's in English, I think so. Cauchy. I think without T, Schwarz inequality. Means that for any xy, we can obtain just, I write in more difficult form, but then we, after 2 minutes, we simplify it. Yes. Then from this Cauchy-Bunyakovsky-Schwarz inequality, we can prove that this object is norm. So in these terms, so we define this object and we name it Euclidean norm. Euclidean norm. So Cauchy-Bunyakovsky inequality in terms of norm looks like shorter, yes. Who can say me for what vectors x and y you can obtain the equality in Cauchy-Bunyakovsky inequality?
If they're
Pure
collinear,
complex.
I think.
What?
If the vectors are collinear.
Yes. Is vector are collinear or linear dependent, and the partial situations x equal to y. So it is Euclidean norm. So the definition, what is Hilbert space? So the space, a linear space with scalar product, H and scalar product, I don't define it, I don't know why, is Euclidean space. Yes, and if H is Euclidean and it is complete with Euclidean norm, not then we H is Hilbert space. So it is a partial case of Banach space, but norm is not some norm. Norm is have some additional property, not only Cauchy-Bunyakovsky inequality. I just remind you some typical another properties of this norm. For example, we can define orthogonality. X is orthogonal to y if scalar product equals to 0. Then we can define it is arbitrary set. We can define the orthogonal complement. It is all vectors y from H such that for any x from M, the scalar product equals to 0. In real space, we can define the angle between vectors. In complex space, it is we cannot define, but orthogonal it exists. Yes, and a very easy statement. I think I don't prove it. It is easy, and I think you know it. That for any set M, the orthogonal complement is closed linear subspace. It is from linearity of scalar product, and by Cauchy-Bunyakovsky inequality, we can obtain that scalar product is continuous. It's continuous functions for any argument. Yes. From linearity and of scalar product from linear and scalar product is continuous function for any argument. And this is from Cauchy-Bunyakovsky, the continuity. Yes. For property, Pythagore theorem, but maybe Pythagore theorem. If x orthogonal to y, then and 5 parallelogram identity. The sum of squares of diagonals equals to sum of all edges of this parallelogram. Yep. It is number 2. The proof is very easy. You can only use that the square of norm is the square norm by definition of Euclidean norm is scalar product of vector on itself. And then you open the brackets by definition of scalar product. Let's discuss one different, very easy example. Show, please, that this space with norm our so-called Chebyshev all uniform norm. So, but on the interval we must change. We can change supremum on max. So we can consider maximum for x is not Euclidean. How we can show it?
Well, maybe just show that the parallelogram law doesn't hold.
Yes, the general approach, find two elements for which parallelogram identity is not valid. So let's try to find two functions for which parallelogram identity is not valid. It is very easy example. It is So you must know only that don't take linear dependent functions. Yes, collinear functions is useless. So the easiest example of function is constant. Yes. So first function I take as identity 1, and second function what? What we take? The next step of after constants.
The identity function.
No, well, what? Ix, yes? You name
Yes,
it.
that's the
Okay.
identity function.
Okay, identity function. Good, good. It is easy to see that on the interval 0, 1, the norm of f equals 1, the norm of g equals 1, the norm of f plus g equals 2, and the norm of f minus g again equals 1. Yes. So if we try to write the program identity, you can see that 4 plus 1 must be equal for 2 plus 2. So it is not valid. So it is not Euclidean. Okay. So let's prove first here. I think it is sufficient theorem. But okay, let H is Hilbert space. H0 is non-trivial subspace. Non-trivial is not zero space and is not all space. Yeah. And X is not from H0. Then exists X unique element X0 from H0 such that this norm gives us distance. I just define what is mean. From X to H0 and X minus X0 orthogonal to H0. As it is from school we know that the shortest distance is the orthogonal.
I'm sorry. Is this the theorem on separating hyperplane?
What? Yes. No, it's about this, yes. Or not. Maybe you mean Banach theorems, but Banach separating of convex convex sets. It's about a theorem on orthogonal complement, maybe. Some definition. What this definition? Let X row matrix space M from X some set and X from our matrix space. Then distance from element X to set M is infimum of matrix between X and Y when Y lies in M. Is it clear? So the distance between set is an infimum of matrix. So it is infimum of X minus Y, Y belongs to H0. So let's prove it. Is it known theorem?
For me, it is not.
Okay, I prove it. It is not. It is difficult. So, oh, but I forget one thing is non-trivial and important property closed. It is if it is not closed, we take closure. So check, please. This make correct.
H0 is closed.
Yes, yes. H0 is non-trivial and closed subspace. Non-trivial and closed subspace. I can check it. Is non-trivial and because it is important property and closed subspace. So why? If with Fx is not from H0 and H0 is closed, so it is not a limit point, yes? X is not a limit point, so it is closed. Then we obtain that the distance between X and H0 is a positive number. Is it clear? If distance is 0, then it is by definition we obtain that it is a limit point. And this number is positive. So from these two assumptions we obtain. So by definition of infimum, we can construct there exists sequence yn elements from H0 such that the norm tends to the D. Yes, by definition of infimum. So then for any epsilon positive, there exists number n capital which depends on epsilon, such for any indexes n m greater or less than n. For any one index. You can obtain two-sided estimations. It is greater than D because D is an infimum, but you can obtain the upper estimations. Yes. So take n m large, sufficient large, and consider such geometrical interpretation. So I make a picture. It is subspace H0. This is our element X. Here Yn, here Ym, and we construct parallelogram. So by parallelogram identity, we can write. So one diagonal is this diagonal. Another diagonal.
Sorry, what is the fourth point? Like you've just drawn 3 points. What is the fourth point?
What?
I'm sorry.
So it is Yn and Ym. They are from
yeah. I understand now.
And
Sorry,
then
I'm a bit...
I write this. I construct the parallelogram on these two edges. This first diagonal, I write formula, and it's maybe say clear. Then another diagonal at this. Yes, and it is equal x minus yn square and double plus and this. Is it clear, this formula? It is a parallelogram identity. It is diagonals and these edges. And this is some picture for this formula. Then what we take? You put this term to the right side and take away the factor 2. And you can write it as follows. It is 2 double 1 each, double another each, and you take away the factor 2, minus 4x minus square. What estimation we can obtain by this? Put it here. It is less than 2 di plus epsilon square plus 2 di plus d plus epsilon square. But this is, you can see that this vector is from h0, so this norm is d. Yes, d is infimum of distance, and here we obtain some distance between x and some vector from h0. So if we subtract the minimal possible, then we obtain this, and you can calculate that d square is eliminates. Yes, here we have 2d squared, here 2d squared, and this is minus 4d squared. So if I calculate here 2, 4, 2, 4, 8d epsilon minus plus, sorry, 4 epsilon square. This is, yes. And you can see that it tends to 0 as epsilon tends to the 0. So what conclusion we can make about our sequence Yn? Is fundamental. So you can see we use a special property of our Euclidean norm. We use the property of parallelogram identity. So it is fundamental. We immediately obtain that there exists a limit. So let's define this limit as x0. So there exists an element which gives us a distance. How we can show that it is unique? If we exist some another element when we have non-correctness. Of course, this sequence is not unique. Yes, sequence Yn such that this difference tends to the d is not unique. But again, if we take another sequence Zn from H0 such that x minus Zn tends to the d, we can consider new parallelogram x, Yn, and Zn, and write the parallelogram identity. Parallelogram identity for Yn minus Zn square and the same estimations. 4 minus yn plus zn over 2 square. And again, we obtain that it is less than. So the limit yn coincides with the limit zn. So this limit is unique. We have a unique element which gives us a distance, yes? Which gives us a distance from element to the subspace. And why it is orthogonal? So we have not only the claim of our theorem that it exists unique, but it is orthogonal. Why it is orthogonal? Let's consider let's consider vector x which depends on t. It looks like x minus x0 plus tz for arbitrary z from h0 and t is real number. And consider function ft, which we define as the square of this norm. And we know that if t equals 0 is a minimal point, is a minimum point for function f, yes? Because it is some element from h0 and x0 gives us the shortest distance, the smallest distance. So write formula for f in details. It is easy to see that it is equal x minus x0 square plus two real parts. Real parts, what, x minus x0 z, because we have x minus, I don't consider all sums. Three elements here, three elements here. If we write the full color product, we obtain nine terms. I want this difference will be as general element, and you consider that we have scalar product between this element with z and with z and this element, but in complex space it is two conjugate numbers, so we obtain the double real part and multiplicate it on t plus t square on norm z square. If this formula is clear, and f t, because t equals to 0 is a minimum point, so the derivative equals to 0, yes, in this point. And the derivative, it is just two real parts. Then we obtain the real part of this scalar product equals to 0. In real space, it is sufficient. We obtain, so in real space, it is means that this difference x minus x0 is orthogonal for any z from h0, yes? But in a complex space, what we do, what we can do in complex space, in complex space, we make a change z on imaginary unit on z. And then real part change to the imaginary part. And from this, we obtain the imaginary part equals to 0 again. So we obtain that x minus x0 z equals to 0. So x minus x0 orthogonal to z. And the sequence of this theorem, corollary, sorry, so corollary, that H is Hilbert space, H0 is closed non-trivial subspace, then exists H1 close to, this is important, close to subspace, such that we can write H as a direct sum of two closed subspace. Moreover, H1 we take as orthogonal complement. Orthogonal complement. So if x lie in H0, then we can write it as x plus 0. Yes, it is from H0, it is from H1. Oh, it's from H orthogonal. And if x is not from H0, by theorem exists, previous theorem, exists x0 from H0 such that this norm is distance. For our situation, it is not important that it is just a distance, but important that this vector is orthogonal to H0. So define x1 as, and we obtain that x equals to x0 plus x1. So we have decomposition of space for any, we have decomposition for any vector, So and it is orthogonal sum, yes, and orthogonal sum is direct. Is direct. It is obvious. So that's all. We just construct the closed complement. So go to the basis. So orthogonal systems, next topic. Orthogonal systems. In Euclidean and Hilbert space. Of course, more important for us is a Hilbert situation. But some theorems are valid in Euclidean, not complete spaces. Wait, systems in Euclidean and Hilbert, what I write? Sorry, spaces. I don't consider unseparable situations, so we always consider an infinite dimensional separable space. So consider only H separable Euclidean space, of course, infinite dimensional, because if the dimension is finite, so it is linear algebra. By definition, we have a basis. Yes, by definition of the dimension, we have a basis in this space, and power of this basis is n. It's fine. So definition: system ek from 1 to infinity is orthonormal, and we use such brief for this orthonormal system if the scalar product between two elements gives us Kronecker sample. Yes? Delta Ig, Kronecker symbol. Then for any x from H, we can obtain numbers xk, which is a scalar product between x and ek. Fourier coefficients. So we can define Fourier coefficients in abstract situation, not for sine or cosine systems, but for any orthonormal system. And we can consider Fourier series and our goal to understand that this series in Euclidean space gives us a representation of x. So first theorem, that H is separable.
I'm sorry. This is a meaningless correction, but Fourier spells differently. It has R at the end. Fourier,
Okay, thank you. For
like that.
this, yeah? This correct?
No. Yeah. This one is correct.
Thank you. Thank you very much. My English is not so perfect. Let H is separable Euclidean. Finite dimensional. Ek is orthonormal system. Then for any x from H, the sum of squares of Fourier coefficient less or equal to the square norm. The norm, of course, Euclidean norm. So it is Bessel inequality. Bessel inequality. Proof. I begin from some additional statement. It's like lemma. It is simple, but it is important. We use it many times. We will use many times. Define x sub n, so index up. It is partial sum. So I don't, I defined it in the beginning. So here, xk, it is Fourier coefficient, always will be. So here, xk, it is Fourier coefficient. Then we have such property of these partial sums. the difference between element and its partial sum is orthogonal to its partial sum. It is easy to check because let's write it. I write different indexes, especially, and let's use the definition of our scalar product. So this x on this sum, it is sum for G1 n by definition. So it is second place. So xg conjugated will be and x here g. And second sum for I and for G from 1 to n, and we have xi, xg conjugate, and scalar product between two elements from orthonormal system, and we know that it is Kronecker symbol delta ig, so we obtain one sum, so it is xg square because of course it is xg sum for n, and minus the same sum, so it is 0. So it is 0. And then we prove the theorem x square by Pythagorean theorem. It is, we prove that the two elements are orthogonal, and we can use Pythagorean theorem. Then it is we take away one term, non-negative, so we obtain the inequality. And for this, we write here, looks on this formula, and we obtain that it is just the same calculation. You can obtain that the square norm of partial sum is just the sum of squares of absolute values of Fourier coefficients, and we can obtain it for any n nature. So you take a limit. Left side is not depends on the n. So if we take limit, we obtain our best, not our, but best inequality. Okay, yes. Remark. Bessel inequality show us that the sequence of Fourier coefficients lies in L too small. Bessel inequality gives us more information. We have precise estimation. The sum of square root, the sum of squares less than the square of norm. But simple interpretation that the Fourier coefficients lies in L2. Some inverse version of Bessel inequality, but we need a Hilbert space theorem. I think it is RIS, or inverse of letters. RIS. Yes, it's correct. RIS and Fisher theorem. So let H is Hilbert space. EK is orthonormal system in H, and of course it immediately obtained that the dimensional of H is infinite, and let's consider the sequence from L to small. Then exists X from H such that xk just Fourier coefficient of this element for this orthonormal system. Proof. What we do, I'll again consider partial sum. Let n greater than m, and consider this. It is up. We do this calculation, so I write it briefly. You can check it. It is just this sum for g from m plus 1 to n. And of course, it tends to 0 as nm tends to infinity. So what we can say about this sequence of partial sums? It is fundamental. It is fundamental, so there exists a limit. We consider Hilbert spaces. We consider the complete situation. So exists limit. Define it as x. It's clear that Fourier coefficients of x is just xk. Yes. So we have all instrument to prove existence of basis and separable Hilbert space. But I introduce some additional notions. That's a definition. Let X is norm space. System EK is complete or is closed if the closure of linear span gives us X. This closure of linear span. Because we take the procedure of closure and name this system as closed. What is the difference between closed space and basis? Remark. Again, by default, if I say basis, I mean only Schauder basis. Yes. If EK is closed, is basis, then of course EK is closed. Because by definition of basis, we can important thing, approximation. Tends to the 0 as n tends to infinity. So we can approximate element. It is from linear span, yes. linear span, and the approximation to the zero of difference is just a closure, yes? So it means that from basis we immediately obtain that any basis system is a closed system. Inverse is not correct. Example. Weierstrass theorem. If we can ek of x, we consider xk. K is natural and zero. Where? In this space. By Weierstrass theorem, it is closed. It's closed because it's closed by I think the theorem, but not basis. Difference between closed system and basis. For basis, we have a theory. We have a representation. For basis, we have a priori representation. So if you need to obtain more precise approximation, what we need to do for basis? If we have a basis and you, for example, you obtain that it is less than epsilon, yes? We have approximation as epsilon. What we need to do to obtain, for example, epsilon over 2, if we need to obtain more precise approximation? Answer is simple. We must take n1 the same series and n1 greater than n. But for closed system, we have no the base, the series. For closed systems, we have not representation. For x as sum. Is it clear? Following definition. Let H is Euclidean space. System is complete. Don't miss it with the notion of complete space. I define the notion of complete system. Is complete if for any x from H from equalities equals from for any k, it implies that x equals 0. So if exists element which is orthogonal to all element of our system, then it is must be 0. And theorem, one Fortunately, I think we have no time to prove it. Maybe we take some minutes from seminar for finish it. Theorem. Let H is separable Hilbert space infinite dimensional. EK is orthogonal system. So I take this brief writing. The following are equivalent. Then the following are equivalent. First is closed. Is complete. Is basis. Fourth, for any x from H we obtain the Parseval equality. For arbitrary orthonormal system, we have only Bessel inequality, but for basis, we have Parseval equality. Okay. Proof. Idea, we show such cycle 1 to 2, from 2 to 3, from 3 to 4, from 4 to 1. This idea is clear, yes. If we show the cycle, we show that from any statement we can obtain another statement, so it is equivalent. First step from 1 to 2. So let it is closed. And x not 0 and x orthogonal for a k, for any k. By the closed of system, closeness of system, we can find there exists linear combination. C, K, E, K for some n, not in this order, but some, it is not a basis, some sub-indexes n, K, such that there exist sequences of linear combination which tends to the x. Here, when change what we change n, c, k, e sub-indexes n, k. Yes. So then we can write n x as limit of such linear combinations. I think it is clear. It's limit on n, c, k, and sub-indexes n, k. But we can, for n, c, k, and sub-indexes n, k, we can write n x as limit of such linear combinations. I think it is clear. It's limit on n, c, k, and sub-indexes n, k. But we can, for n, c, k, and sub-indexes n, k, we can write n x as limit of such linear combinations. obtain that these scalar products equals for what? Sum ck e n k x, and this is a 0, so it is 0. So we immediately obtain that it is 0. Is it clear? So second step, from 2 to 3. From 2 to 3, why it is basis? So take x. Of course, all orthogonal system is linear independent. Yes, take x, construct Fourier coefficients xk equals to xak, and then consider sum if this sum is not x, define it as another vector, so y it is this sum. Then consider this scalar product. It is equals xk by definition, and it is equals to xk by definition of by construction of y. So it is equals to 0. So by completeness of system, it is 0. So xy equals to y. So step from I take pair minus and finish the proof. Of course, yes. Take pair of minutes and finish the proof of this theorem. What we need to obtain. So yes, for any x by definition of basis, for any x, we will know that x is xk ek. It is sum, and x is a limit of partial sums. Yes. So then we obtain that the square of norm equals to this scalar product, and then change one of the vector on its partial sum. On each partial sum. Then by properties of scalar products, we can write it as sum xk and scalar products ek on x, and of course this element is conjugate Fourier coefficient. So we obtain that it is limit of n tends to the infinity of these partial sums. But by definition of partial sums, we obtain that it is just and the last step, fourth step, from 4 to 1, yes? But I make some trick. We show another. We go by this. This is by definition. We discuss it, yes? By definition of basis and closed system. This we show as usual. Take x from h, xk, it is Fourier coefficient, and let the sum of Fourier sum is not x, so it is y. Not x, we must show, but the all series we write are converged by Bessel inequality because xk is small, Fourier coefficients are from L2, so the series are all series are converged. And then again, use Parseval equality. We know that this norm equals to these scalar products. Yes, the sum of the Fourier coefficients. It is from for property by Parseval identity, and this is again equals x ek minus y ek, and again this equals to xk by definition of Fourier coefficients, and this is equals to ek by construction of y. So it is to 0. From Parseval equality, we know that x equals to y. So that's all for theorem.